So a little recap of what we closed off with on Tuesday. So we talked about period, wavelength, frequency. And remember, our abbreviation for period was a capital T. Wavelength was that lambda, the upside down Y looking thing. And frequency was just a little f. And there's a big relationship. The relationship between frequency and period is the frequency is the reciprocal of the period, or the period is the reciprocal of the frequency. Either way. And the big relationship between wavelength and frequency is the velocity of our wave is equal to the wavelength times the frequency. And for some of our waves, most of our radio waves are traveling at the speed of light, so that velocity becomes 300,000 kilometers per second. Little c represents the speed of light. Which is 300,000 kilometers per second. Or 300 million meters per second, if you wanted to express it that way. Our angular velocity, we're talking about rotational now as we rotate around a circle. Looking at a rotating object. That rotating object is what we call, has what we call angular velocity. So I have something here that is pivoting around a center here, rotating in a circle. This could be the crankshaft of a motor, could be the shaft of an electric motor, a pulley on an electric motor, could be a planet orbiting around the sun. They all have some form of angular velocity because they are going in circular motion. And it does have to be circular motion. So we identify something called omega, or not, that is actually small omega. It looks like a kind of a plump W. That is the symbol for angular velocity. It is equal to the degrees, the angle that we've rotated, divided by the time. Now let's compare that to linear velocity. In linear velocity, the velocity, v, is equal to the distance traveled divided by the time. So what's happening here is, instead of looking at the distance, we're looking at the angle that's traveled and dividing it by our unit of time. We talk about our frequency now in terms of this. Our frequency is the number of the angle, the number of rotations that happen in time equals 1 second. So if we get more than a full rotation, our frequency is bigger than 1. It's possible to have less than a full rotation, less than a complete cycle in a second. Distance, yes. And technically I could have used the letter S there for displacement, but it means the same thing. Distance moved. Theta is usually represented in radians. So remember, 2 pi radians is equal to 1 complete circle. So that's going to be 1 complete cycle. So frequency can be calculated in a lot of different ways. Frequency, remember, I kind of set it up here, but I didn't put it in terms, is the number of cycles per second. So one formula for frequency is our frequency can be our angular velocity divided by 1 second over, actually I got that wrong, that should be omega. The angles, the degrees are radians, in this case radians is what we would normally use, per second divided by 2 pi, because 2 pi is the 1 cycle. So the angle that is rotated in a single second divided by 2 pi is how many full rotations or how many full cycles. For example, if we have an object that is rotating 8 rotations in 4 seconds. 8 complete rotations. Now that's an alternative. I didn't put that alternative up here. This is dividing by the 2 pi is getting how many rotations. So one example for frequency is the full rotations divided by the seconds. That's the second formula I'm going to use here. So for this example, we have 8 rotations in 4 seconds. That is 2 rotations or 2 cycles per second. That would be my frequency. If I gave you the example, oh, we're going to rotate 18 pi radians in 2 seconds. That's going to use this top formula up here. The frequency is going to be found by taking that angle 18 pi radians divided by the number of seconds. This is radians in a single second. Well, this is 2 seconds, so we're going to have to divide by the 2 seconds. Then we're going to divide that all by 2 pi. So first we'll start out up here. 18 pi radians divided by 2 seconds. What's 18 divided by 2? 9. So that's 9 pi radians per second. That still has to be divided by 2 pi here. So the pi's cancel out. What's 9 divided by 2? 4.5. And the radians cancel. There's radians implied to be canceled out there as well. So that's 4.5 per second. That is my frequency. 4.5 cycles per second. So those are 2 forms of the formula to find a frequency. I can also find a frequency as my angular velocity divided by 2 pi. So an example of this, let's say I have something that is rotating with an angular velocity of 48 pi radians per second. My frequency is going to be that 48 pi radians per second divided by 2 pi. So again, the pi divides out, the radians divide out with it. What's 48 divided by 2? 24. So that's 24 per second, or 24 cycles per second. That is my frequency. From that last formula, frequency is equal to omega, the angular velocity, divided by 2 pi. We often solve for omega, the angular velocity. How would I solve that for omega? I'd multiply both sides by 2 pi. Cancel that out. So 2 pi times f is equal to omega. So that is one way that the angular velocity is often expressed. Because of that expression. Now, why is it that in telecommunications, or in broadband technologies, we're talking about angular velocity and things rotating? Well, you do have rotating motors and stuff like that that you could deal with. But more importantly, your sine wave, your signal, AC voltage and AC current, use this formula, this type of a thing to track their cycle. Remember, we said that what's really happening there is it is a unit circle, and we are rotating around that unit circle. That's what produces that sine wave. That's why it's cyclic. It keeps going on and repeating over and over because it's going around and around that circle. Well, the voltage at any instant, we're going to call it instantaneous voltage, is described. Now, we talked about peak voltage. So that voltage with the little I there, that's one way of representing instantaneous voltage, or V with T in parentheses is another way of representing instantaneous voltage. The formula for that, V little I, is equal to our peak voltage times the sine of our angular velocity times T. Omega is 2 times pi times our frequency. Remember, the frequency for AC power is usually what? 60 hertz. So typically, omega is going to equal 2 times 60 times, or 2 times pi times 60 will be 120 pi. Is our typical value for omega. Now that is in radians, not degrees. So we've got to make that shift now, where you change your calculator over to radians. Or if we wanted to put it in degrees, this is radians. If you want to convert to degrees, remember it is 120 pi radians over 1. We're going to multiply by 2 pi 360. So the 2 pi cancels out. That leaves us with 1. Here the pi and divided by 2 leaves us with 60. So 60 times 360 is 21,600. That would be degrees per second. So you can see why we typically stick with radians. That's instantaneous voltage. Instantaneous current. which is just the current at any instant in time, is I with a little I, or I with the T. That instantaneous current is going to be our peak current times the sine of omega t. Now, peak voltage is often specified. For the 120 volt or 110 volt power, peak voltage is usually what? You guys remember? 170. 170 volts is peak voltage for 120 volt power. Remember, what we call 120 volts is actually 120.19 or 120.2 approximately volts. That's usually spelled out. Peak current is usually found using voltage peak equals current peak times our resistance. I'll take out that and put in R times our resistance. So examples. If V peak equals 170 volts, find the voltage 3 seconds after the start of a cycle. Now, first thing we have to do, well, let's write out the formula here. Our instantaneous voltage is going to equal our peak voltage of 170 times the sine. In parentheses here, I'm going to put omega is 120 times pi times t, which is 3 seconds here. Now, first thing I'm going to have to do is I have to go on my calculator and I have to change it into radian mode. So I press the mode button. I go down to radians and I select radians. So now in radian mode. For you guys, do you have a DRG key? Yep, so press that until it says rad on top of the screen. Okay, so you're now in radian mode. So we're just going to punch this in then, just like that. 170 times the sine, in parentheses 120 times, I'm actually going to use the pi key for this one, times pi times 3 and close my parentheses. Now that negative 4.76 times e negative 9, that is negative 4.76 times 10 to the negative 9th, which means I'm moving this decimal point 9 spots to the left. So that is 0.00000000476 volts. That's actually a fake reading, because at a whole second, the voltage should be 0. So that's a quirk in the calculator. Let me see if it does anything different. I'm sure if I use 3.1. 0? Okay. And it should say 0. Yeah, see if I use 3.14, it really throws it off. So you have to use the pi key. But yeah, that's just a quirk in this calculator. For some reason, it does that when you do larger repetitions of pi. There's something wrong in the pi in this calculator, so if you multiply by large numbers, it's off. Any whole second, remember, it's 60 hertz. So what that means is, in 1 second, there's 60 of these cycles, right? Well, the end of that cycle should be at 0 volts. So 60 full cycles would put you back at 0. So every second, you should be back at 0. So let's look at something a little more interesting than that one. Peak voltage is still 170 volts. Find the voltage. And we're just going to assume here for these examples, we're going from the start of a cycle, so I don't have to write that out every time. Find the voltage at 32 milliseconds. So our voltage, instantaneous, 170 times the sine of 120 times pi times, now my 32 milliseconds has to go in as 0.032. Good. So there we are. 170 times the sine, 120 times pi times 0.032. Okay, negative 81.90. Did you guys get? Yeah. Let's say our peak current is 40 amps. Find the current at 250 microseconds. So our instantaneous current is equal to our peak current of 40 times the sine of 120 times pi times what? 0.00025, right? Perfect. So 40 times sine 120 times pi times 0.00025. 3.76 amps. Have you guys try one here quick. So if I give you the peak current is 50 amps, find the current at time equals 55 milliseconds. So find that one on your own for quick. See what you find. $47.55 is what you come up with? I can buy that. Okay. What if we shake things up a bit? we find the equation for instantaneous voltage if the frequency is 25 hertz. Okay. How does that change our formula? Well, I've got to take out that 120, right? So I have to go back to that basic formula. So VI equals voltage peak times the sine, and it's going to be 2 pi times 25 times T. Remember, this 120 that we were using here, 120 pi I should say, is really 2 times pi times the frequency. And the frequency was usually 60 hertz. So now since we changed our frequency to 25 hertz, we're going to have to adjust it. So this is going to become, instantaneous voltage is V peak times the sine. Well, 2 times 25 will be 50 pi times T. So we just have to adjust the formula for that change in frequency. Find the equation for the instantaneous current if the frequency is 75 hertz. So again, we go back to that basic equation. The instantaneous current is the peak current times the sine of 2 pi f times T. What goes in for F? Frequency is 75. So this is 2 times pi times 75 times T. So that's going to become what? The instantaneous current is the peak current times sine. 2 pi 75 becomes what? You multiplied in the pi. We usually just do the 2 times 75 is 150 pi. Yeah, if you multiplied it out, 150 times pi would be 471 point something. But yeah, it's usually more precise if we leave the pi in there. Well, how about going the other direction? If our peak voltage is 170 volts, find the first time in the cycle that the instantaneous voltage will equal 120 volts. So we're starting out with that same equation. VI equals VP sine. Now we're going to assume the 60 hertz again. So we're back to 120 pi here times T. And what we're going to put in there, the instantaneous voltage is 120 volts. Peak voltage is 170. So times sine of 120 pi T. So the first thing we have to do is divide by 170. So we've got 120 divided by 170. This is going to be 0.7059. Now, I'm going to leave that in the calculator. I'm going to write down 0.7059. The 170 is gone here, so that equals the sine of 120 times pi times T. But notice I'm not clearing my calculator. I'm leaving it in there. Because what's my next step to solving this? Inverse sine, right? That's how we get rid of the sine. So I have to take the inverse sine of that number. So I'll cancel out the sine over here. leaving me with 120 pi t. But more importantly is what's happening here. I'm leaving this in my calculator so I can do second sign and then second answer. Tell my calculator to take the inverse sign of that previous answer, which will give me 0.78367. 0.78367. Now that's radians, remember. Now what do we have to do to solve this for t? I have to divide by 120 pi. On your calculator, the way you're going to divide by 120 pi, I'm going to use that previous answer. I'm going to divide by, I have to put it in parentheses, 120 times pi. Close my parentheses. I get 0.00208. That is a time in seconds. So that is saying is 2.08 milliseconds will be the first time into that cycle where that voltage is at 120 volts. Does that make sense? A little bit? Let's do another one. Let's say our peak voltage is 170 volts. Our resistance is 34 ohms. Find the first time in the cycle that the current is at 2 amps. Now notice I asked for current here, so I'm dealing with the instantaneous current is equal to the peak current times the sine of 120 pi times t. Well, what's this peak current here? Peak current is equal to peak voltage divided by resistance. So that's going to be 170 volts divided by 34 ohms, otherwise known as 5 amps. Correct? Yeah. Questions so far? We're good so far? Okay. So now I'm just going to fill in. I want this to be at 2 amps for my instantaneous. My peak is at 5. Sine of 120 times pi times t. What's my next move going to be? Divide by 5. So 0.4 equals the sine of 120 pi t. Then what? Inverse sine. Cancels out the sine. So we're doing an inverse sine of 0.4. This is going to give us 0.4115. Over here, the sine and inverse sine cancel out. That's just 120 pi times t. What do we have to do now? Divide by 120 pi. So that's gone. That's t. Now remember, on our calculator, we take that 0.4115 divided by, and in parentheses, 120 times pi. Close the parentheses. 0.00109. And of course, that will be labeled seconds. So that means we're looking at what? 1.09 milliseconds. Last thing I'll show you, then I'll let you guys head out and get to work. Sketch the voltage. If voltage peak equals 90 volts and frequency equals 40 hertz. So this sketch on my graph, what's my amplitude going to be at? Well, if it's a 90 volt peak, I'm going up to 90 volts. I'm down to a negative 90 volts. What is my period? Well, frequency is 40 hertz. Period, remember, is 1 over the frequency. So 1 divided by 40 is 0.025 seconds, right? So it is 25 milliseconds is a period. So that means 25 milliseconds is 1 complete cycle. So we start at 0. Here, this is going to be 12.5 milliseconds. Where did I get 12.5 from? Half of the 25. It's going to reach its peak voltage at 6.25 milliseconds. How did I get that? 1/4 of 25 or half of the 12.5. Because remember, a sine wave, it reaches its peak at 1/4 of the cycle. It's back down to 0 at half of the cycle, right? Now in here, this point, of course, this is actually labeled down here, 6.25, right? This point right here, the easiest way for me to find that is to add 6.25 and 12.5 is 18.75 milliseconds. That's halfway between the 12.5 and the 25 is what I'm finding there. There's my wave. So we sketched our waveform of that voltage there. So now if I went out to 1 full second, how many of these waves would there be? 40 per second. Right? That's what that frequency means. What do you guys think? That's a lot of stuff. Okay, in the packet you guys have, in the AC current packet, alternating current, it is page 371 through 372. 1 through 53, the odd. Enjoy.